from Liverpool. I think already Keith has told us that he's going to actually go into the details on one of the, the important aspects of the center. So please, Alexander.
Thank you. Hello, I'm going to talk about several mathematical models of structured stents in blood vessels. And this work is based on the effort of an interdisciplinary group, which includes a group from mathematics department, then surgeons and interventional radiologists and engineers. And of course, EPS receives support through the grant which we have in Liverpool is gratefully acknowledged. There are two classes of problems I'm going to talk about. One of them is related to so-called abdominal aortic aneurysms, and another class is related to periodic stents in cylindrical blood vessels. And if you think of mathematical models for stents, there are three different stages which can be looked at separately. One is installation of stent, and it's a highly nonlinear, very challenging problem. Second, response of stent to different loads, and I will simply refer to this as the dynamic response of a stented system. And the third problem is the network response after installation of stents. So I will be mainly focusing on the second part. So how did it all happen? In Liverpool, we have a very active vascular group, and it just happens for one reason or the other that in the north of England, expertise in vascular surgery is quite impressive. So if you go to places like Dudley, Wolverhampton, Stoke-on-Trent, or some places at Merseyside, the number of vascular patients is quite substantial, and of course expertise in the hospital is significant. The procedure I'm going to talk about is called EVAS, that's endovascular sealing, and it was introduced by an American-based company, Endologics. And one day, two colleagues, Francesco Torella and Richard McWilliams, who are the vascular surgeon and interventional radiologist from the Liverpool Hospital, came to us and said, well, we really need some advice. And there is a procedure, EVAS. That time we never heard about this. And we follow so-called instruction for use. Everything is good on the installation, but after all, these components of EVAS system, they move. Could you tell us everything about forces, all possible forces that can act on this system? And the short answer is no. I mean, how could you? It's an extremely complicated system. Geometries are different from patient to patient. It's highly nonlinear. No way. But then, as we spoke about this a little bit later, there was additional information. What they do, they insert two stents enclosed in the so-called endobags, and then they pump polymer into these endobags to hold these stents in place. Now, the mass density of the polymer is 2. You can say, how come? Is it possible to find something lighter? Well, I can't give you the answer to this question for one reason or the other. For them, the answer was no. That was the polymer certified for operations of this type. So the result of this is it's very heavy. So a patient who has this abdominal aortic aneurysm, and it's here, after the installation has additional 1 kilo of weight. And then after it's solidified, well, it's a pendulum. And then I thought, well, I can do pendulum. And of course, it's a fairly complex pendulum, but we can set a spectral problem and we can see how these things move. And of course, it's also possible to solve a static problem and see how these things move if you load it with a force like gravity. And that's what we did. Of course, there were some challenges related to setting up the boundary conditions and transmission conditions, because it's a multi-scale system with several components, but the idea is exactly as I described. So then, of course, I will talk about the problem, but what we did, we pretty much introduced classification for these systems, and now surgeons have a catalog, and they can take this aneurysm on their iPod and look at it and see how it moves. And then the components of this EBAS system, they move, and they can see how they move at different frequencies. And then if they have another geometry, that's okay. All they do, they just select another geometry. And of course, the geometry is not something which you take as idealized geometry. The geometry is taken from the CT scan. So as you can see, it moves, and that's what surgeons have now. So this is a static picture. It's a snapshot, but you can have dynamic response, and you can see the eigenmodes and the eigenvalues. Why is it important? So these are 3 examples, and these are real geometries, real patients. So the first eigenmode is 8 Hertz. If a person travels on the public transport, they can experience input of up to 20 Hertz. So if you have a transatlantic flight from London to JFK, New York, you would experience with a probability of 80% so-called clear air turbulence, and this would give you up to 20 Hertz. And therefore, this kind of thing can start moving, and that's one example. Then the other class is related to dynamic response of cylindrical blood vessels with stents. And in this case, the problem is again very complex. If you take a blood vessel and just look at the model, it's extremely complex, because if you try to model it based on partial differential equations with constant coefficients, or let's say time-independent coefficients, that wouldn't be right. But if I simply look at how it behaves, even in a simplistic case, the blood vessel is adaptable as soon as you introduce stent. The stented section is not adaptable anymore. So the coefficients of PDEs for the stented section are not time-dependent anymore. So the biological system does not respond as it used to. And of course, then our simulations show very clearly that if you run this kind of model around the stented region, there is some perturbation in the fluid flow and also in the wave response of the vessels, of the walls of the vessels. So it's a fluid-solid interaction problem. Why is it difficult? Well, if you try to set it up as a fully coupled transient problem, even starting the computation is a challenge. So you have to run additional auxiliary problem to generate a initial state. And of course, it's a 3D geometry. You can spend a week running the simulation. You will get some result, and this result will be inconclusive in the sense that surgeons, medical practitioners will not necessarily get anything from it that they can use. So these are different shapes that you can see when waves propagate through a periodic structure reinforced by, well, stent-like system. Now, several papers were published. The problem about abdominal aortic aneurysm was published in Scientific Reports of Nature, and then there was a series of papers on waves and fluid-solid interaction in stented blood vessels, published in the Proceedings of the Royal Society, and in particular, reflection and transmission was analyzed. So now let's look at this two classes of problems. So that's abdominal aortic aneurysm. This is the CT scan. We would typically get a DVD for a patient with full three-dimensional geometry. So we have very detailed information about the geometry. Then this would be programmed in the PDE package, and there are different possibilities, COMSOL, abacus, so that's finite element computation. And what we are looking for is discontinuities related to the motion. And vascular surgeons refer to so-called migration and separation. And these were the features that we were looking for. Of course, you can expect the answer that if the aneurysm is too big, then the eigenfrequencies are going to be really low, and then it's likely that there will be some motion of components. Well, it's not that simple, because in addition there is a thrombus, and it has different material parameters. It's much softer, and all these things have to be taken into account. So then that's the overall structure. This is where it all happens. It all happens between the so-called renal junction and the iliac junction, where the aorta splits into two arteries going to the legs. And of course, as we analyze it, we can analyze every cross-section. So the results, computational results, allow you to look at the whole motion, including every cross-section. So in this sense, of course, we have made simplifications, and the fluid was considered as acoustic medium, so we did not look into the influence of the fluid flow as such in this spectral problem, and there was no need for that. But the main thing was to answer the question that our medical colleagues asked us, and they were happy with the model. The model predicted pretty much the results consistent with their observations, and the result was that so-called instruction for use for this procedure has been changed, and this company, Endologics, did not have this procedure licensed in the United States, but it was licensed in the Netherlands and in the United Kingdom, and now this license has been withdrawn as a result of this work and several papers that our medical colleagues wrote on the basis of this work. So these are some sketches for the vibrations and vibration modes for 2 patients. As you can see, geometries are different and the frequencies are different. And of course, we can see not only how they move, but also how the components move inside, because we can take any cross-section in the dynamic regime as it moves. So now this is just again an explanation of how this works, and the importance of this study was that there are 2 procedures commonly used for repair of the abdominal aortic aneurysm. One is so-called EVAR, and that's endovascular repair, and another one EVAS, which is endovascular sealing. EVAR is a little bit more invasive than EVAS, but EVAS, as turned out, had some other drawbacks, and that was the purpose of this study. Then, of course, here we have the table, and we focused specifically on the range of frequencies up to 20 Hertz, and that's really what was the importance. So, well, the lifestyle for a person who had this kind of procedure turns out to be quite important. Now, these are computations related to static loads, and because this polymer is so heavy, even for static loads, these components can move, which we have also identified. And it's patient-specific computation, so as soon as we have the geometry, these computations were done, and then for patient-specific data, recommendation can be given. Well, recommendation is not the right word. Recommendation is given by the surgeons, but we provide them with the information. And so I already mentioned that EVAS system appears to be vulnerable to dynamic forces, and of course this has been taken into account. So this is the illustration of the catalog which we have built, and this catalog gives a very detailed classification. It's a multimedia catalog. It's a PDF file, so it doesn't play, but in the actual catalog, as you click on it, it will show you the motion of this aneurysm sac and the relative motion of its components. And again, another shape, for example, here you can see a certain amount of thrombus accumulated, and it's a fairly large elongated aneurysm. And this one is again a different shape with a lot of thrombus on the sides, and as you can appreciate, dynamic response would be different. So now let's have a look at another class, and this class is related to reinforcement of cylindrical vessels, or approximately cylindrical blood vessels, by structured stents. One important feature of the structured stents is their periodicity. So there is a periodic pattern, and if you ask why, well, I suppose it's been used for well, for the purpose of manufacturing, and that's just the way it's done. All stents have periodic structure. There are 2 types of stents. One class of stents is used for repair of aneurysms, and usually these are membranes reinforced by sparse stent structure made of shape memory alloy nitinol. And another type of stents is used for stenotic arteries, and these are often very, very dense periodic, very, very dense structured stents with the periodic pattern. And here you can see examples, and here you can see the size as well. Now, they move in different ways. They can expand, that's the easiest way. There is axial deformation, there could be torsion as well as bending. The typical model would be dealing with this radial expansion. But because the blood vessels are not straight, you would look at bending and torsion inevitably at a certain stage. So what we want is to see what happens in the transition regime. What does it mean? You can say, what is the heart rate? Okay, 60, 70 beats a minute. It's very, very slow. There shouldn't be any significant dynamic effect. But first of all, if you look at the pressure profile, it's not sinusoidal. And second, there are transition regimes. What does it mean? Suppose I walk on the street and there's a car coming. So I jump off the way, away from the car, and literally within 2 seconds, my pulse rate would go from 60 beats a minute to 180. 2 seconds, and you have this jump. So you take the pressure profile, expand it in the Fourier series, see what you've got, and then you will see high order harmonics. In reality, stents are absolutely fantastic invention, and the variety of stents is huge, and vascular surgeons do absolutely amazing things with stents. But usually, after they've treated a patient, so the patient has been released from the hospital, goes home, all good. For a year there are no problems, it's all fine. But then they observe and sometimes notice that certain stents get blocked. And in some cases they get blocked more than in the other cases. And vascular surgeons have no answer to that. Of course they have their experience, they have their intuition, but because the market is so diverse and there is there are new products coming on the market all the time, they asked if there is a way to quantify these things. So this model is about dynamic response of stents in the context of transmission reflection. But because we have this periodic pattern, as often happens, reflection is high. If you look at the corresponding periodic structure and you observe that waves within this periodic structure simply cannot propagate. In the waves modeling community, this kind of interval of frequencies would be referred to as a stop band. So you wouldn't see this kind of structures in biological systems, but it's an additional model problem that you would look at. And of course, you can also say, come on, the model is highly nonlinear, and that would be absolutely true. But as soon as you've stented it, stent keeps the shape, and all this adaptivity and nonlinear response for that particular shape, they're lost. So stent makes things very convenient for modeling, but it's not necessarily the best option because the blood vessel is not adaptable anymore. So then there are different ways to model it. Of course, there are very effective models for thin shells with reinforcement, which we used. Then finite element modeling with the Bloch-Floquet conditions, which we have done in 3D formulation with the reinforcement. We looked at different types of stents, and it's again one of the interesting questions. So for example, you can have additional connections that make the system more reinforced. sometimes the corners face each other, sometimes the corners don't face each other. Which one is better? And we have looked at these cases. So then, of course, dispersion diagrams are easy to construct. When I say easy, it looks easy when it's done, but it's doable. And they're very complex, but nevertheless, you can identify some dispersion curves dominated by radial expansion. When I say dominated, it's important because these are not necessarily clean radial modes, but they're dominated by radial modes. And then, as you can see, without stand, you don't have any stop bands. With a stand, you do have stop bands, which means you may have localization. Then, as you look for non-axisymmetric modes, and that would be typical if there is any kind of deviation of the axis of the blood vessel from the straight line, then the band gap is getting wider. And then I showed you at the beginning the movie well, that you can run on your own device, and for vascular surgeons these things can be loaded on their iPad, and you can just see how this stand will react to the wave of given frequency. Stop band, you have reflection; pass band, you have transmission. In fact, of course, it's a model, so it's exaggeration, but it gives you a clear idea of what can be looked at in the transition regimes where frequencies of this range occur. So then, very often, stenting procedure involves more than one stent, and it's quite typical that vascular surgeons look at the section of the blood vessel, and it requires stenting on some longer section. And for them, there is a question: how do you do it? Suppose they don't have a stent of this length. Are they going to put several stents with the overlap, or are they going to put several stents with the gap? Which way is better? I mean, for them it doesn't matter. They can do either way. But which way is going to be better? Well, overlap is better, and you can also see it from this computations. But usually, overlapping or separated stents they create additional band gaps. So here we also used simple one-dimensional models, very often referred to as, well, a version of Kortebek models for the radial flow, and that would be applicable to the membranes reinforced by stents, which would be typically used for repairs of aneurysms. And then you could see dispersion diagram on one side and transmission reflection diagrams on the other side. Blue line represents the transmission coefficient and red reflection. So in this case, of course, the actual microstructure plays an important role. So as you increase the number of cells, then you will see very high reflection in the region which you have predicted from your dispersion diagram. And then we also looked at the sparse stenting systems, and that's a recent paper that came out well, just in January. And in particular here we also looked at overlapping stents. So that's the paper itself. And here, as I said, it's a simplified model. So you have volumetric flow Q and pressure P, and then so you just reduce it in this form. Then you calibrate so that the slope for the 1D simulation agrees with the three-dimensional computation which we have done independently. And then a structure is described by a periodic function C, which is present here. And then, well, for simplicity, we just use it in this form, where C0 and CA are two constants that are chosen to select the required background level from which we start making this oscillation, and they correspond to different biological parameters, but in fact it's just a constant. And this characterizes the way it characterizes the structure of this sparse stent. So the larger S, the more separation you can visualize here. And in this case, for these functions, you can actually compute the average C in the closed form, and well, look at this problem. So here you have two stands, they overlap. Would it be okay? Would it be better to have large region overlap or small region? Well, the answer is small region. And here we go. That's your dispersion diagram for the model periodic structure. This is two-cell overlap. There is a bit of reflection. As you increase the overlap, reflection increases quite a bit. Again, one long stand or two overlapping stands, and the answer is one long stand if you can. So that's another, probably it's a sort of a common sense question, but here you can see the computations which support this statement. So these are other papers, and currently we are working on two papers that will be submitted shortly. We have given presentations on this a number of occasions, including the British Science Festival, and it was in 2017 when we were really working on the development of this model for the abdominal aortic aneurysm. And this, as I mentioned, has generated a practical impact. The work on modeling of the abdominal aortic aneurysm has produced impact leading to the change of the instruction for use for the EBAS system, and that was apparently quite a big deal. And then we have produced a catalog currently used by the vascular surgeons, and it's a multimedia catalog which shows them not only pictures, but they can see how these things move. And well, I'll stop here. Many thanks for your attention.
Any questions?
Perhaps I missed this, but I was just wondering, in your free vibration analysis, what were the boundary conditions? I mean, how was it tethered outside? Or
Okay, that's a very good question, and of course boundary conditions were a challenge, and one particular region is the top region where the contact is, it's a frictional contact, but if it slides all the way through, well, it's already too late. So we used some effective spring boundary condition for that eigenvalue problem, and then of course on the rest it's a Neumann type boundary condition, and then at the bottom is Dirichlet. So you have Robin type boundary condition on the top, Neumann on the lateral surface, and Dirichlet at the bottom, because it's held in place by the iliac junction.
I was just wondering, for the parameters that you have, did you take into account the patient, the information about the patient, like age, gender, BMI, hypertension, these kind of things, or they are independent from the patient?
What we had regarding the patient, we had a DVD. Obviously, we were not licensed to handle patient's file. So the DVD did not have any details related to patient, no name, no age, but at the very end when we were compiling the catalog, we have produced our results, and the medical team produced their medical observations, and they had all this data. So on the stage of comparison, yes, all this information was available. If you're asking about materials parameters, then the answer is no, we use the material parameters available in the literature. So for all these models, material parameters for thrombus, for arteries were the same. Is it a deficiency? I'm sure it is. But that's what is available in the literature. For one reason or the other, it's extremely difficult to get hold of material parameters of diseased blood vessels. Well, I suppose because of the certain procedures that have to be carried out by the experimental team if they would like to take the measurements. So it's just not available in the open literature. But we use the parameters available, and they were the same for all simulations.
It's a related question. How does a surgeon know how to look up the most appropriate item in the catalogue? What is the connection between the catalogue and another patient's data or geometry or whatever it is he has? How does he know what to look up?
Okay. So first of all, before this catalogue was produced, patients ran their operations and they used to make their judgment. They have experience, intuition, and that's what they used. They don't run any codes, any estimates, but this catalogue gives them additional information. So for example, they can look at the patient and say, yes, it appears to be within the limits for the instruction for use. Let's have a look at our catalogue, which is the geometry similar to this patient's. That one. The size is similar, and the prediction was that there would be migration. Maybe we shouldn't use a VAS system for this patient because it's a borderline case, and catalog suggests that there may be complications. So, and in this case, they may send this patient along the channel of endovascular repair instead of endovascular sealing. So that's how they use it. So this catalog is not an instruction, it's an information for them to use in addition to their expertise and their intuition.
All right. Thank you very much, Alexander.
Thank you.